Hello, everyone. Welcome to SleepSpace. Tonight, we will talk about a question that sounds like it belongs in science fiction, yet it's a very real phenomenon in our universe. Can two black holes merge into one? You're about to take a quiet, cosmic journey into one of the most mysterious and awe-inspiring events in astrophysics. This is a story of gravity, time, and space itself, and how sometimes two invisible giants collide and become one. Let's begin by understanding what a black hole is. At its core, a black hole is not an object in the traditional sense. It's a region of space where gravity has become so intense that nothing, not even light, can escape it. The boundary around a black hole, called the event horizon, marks the point of no return. Once anything crosses this invisible threshold, it's lost to the outside universe forever. Black holes are born in different ways, but the most common way is through the death of a massive star. When a star many times the mass of our Sun runs out of fuel, it collapses under its own weight. The outer layers explode in a dramatic supernova, and the core condenses into a black hole. These stellar mass black holes may only be a few kilometers across, but they can weigh more than 10 times the mass of the Sun. There are also much larger black holes called supermassive black holes, found at the centers of galaxies, including our own Milky Way. These giants weigh millions or even billions of times more than the Sun. No one is completely sure how they form, possibly from the merging of many smaller black holes, or perhaps through entirely different processes early in the universe. Now, imagine two black holes drifting through space. They are usually alone, but not always. In some regions, particularly near the crowded centers of galaxies or in dense star clusters, black holes can come close enough to each other to feel each other's gravitational pull. When that happens, something amazing can begin: a cosmic dance where two black holes start spiraling toward each other. This spiral doesn't happen quickly. In fact, it can take millions or even billions of years. As the black holes orbit each other, they lose energy, not in the way we lose energy by slowing down, but by sending out ripples in space-time. These ripples are called gravitational waves. They're not waves of sound or light, but literal distortions in the fabric of the universe, like the ripples you'd see if you tossed two pebbles into a calm lake. These gravitational waves carry energy away from the system, and over time, the black holes inch closer and closer. As they approach, their speeds increase, and the gravitational waves they send out become more powerful and more rapid. It's a final spiral that ends in one of the most extreme collisions known to science: the merger of two black holes into one. The moment the two black holes finally collide, they form a single, larger black hole. But this new black hole isn't just the sum of the two original ones. Some of their combined mass is converted into gravitational energy and radiated outward in that final, violent moment of merger. This is an event so powerful that it can briefly outshine all the stars in the universe, not in visible light, but in gravitational waves. This isn't just theory. In 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the very first time. The source? Two black holes merging over 1 billion light years away. It was a scientific revolution. Until that moment, black hole mergers were predictions on paper and simulations on computers. Now they were a measurable, observable part of reality. But before we go further into how these mergers work, let's pause and think about the sheer scale of this. These aren't small objects colliding. A typical stellar mass black hole might be 30 times the mass of our Sun, packed into a space smaller than a city. When two of these merge, the result might be a black hole 60 or 70 times the mass of the Sun, though a few solar masses are lost as energy. And when supermassive black holes merge, we're talking about events that involve millions or billions of solar masses. These are the loudest, most energetic events in the entire universe, but we can't see them with our eyes. We hear them with our instruments. We feel them in space-time. Let's also consider how the two black holes find each other in the first place. In many cases, they are born as a binary pair. This means two massive stars orbiting each other in a tight system. When both stars eventually die, they each collapse into a black hole and continue orbiting. These systems are incredibly stable, and their slow spiral inward is driven by the emission of gravitational waves over millions of years. In other cases, black holes may find each other later in life. In a dense stellar environment like a globular cluster, random gravitational interactions can bring two black holes into orbit around each other. These encounters are rare, but they happen. And when they do, the countdown to a merger begins. The merger of black holes doesn't just result in a larger black hole, it also leaves behind a signal, a unique gravitational fingerprint that allows scientists to determine how massive the black holes were, how fast they were spinning, and even whether they were aligned or tilted relative to one another. And one more surprising thing happens after the merger. The new black hole can recoil or kick across space. This happens because gravitational waves aren't always emitted symmetrically. If one direction has a slightly stronger emission than another, the merged black hole can shoot off in the opposite direction, sometimes at thousands of kilometers per second. In theory, this recoil could even eject a black hole from its host galaxy. We'll explore the details of that in a moment, but for now, rest easy knowing that black holes aren't just cosmic vacuums endlessly consuming everything. They are dynamic, interactive, and sometimes surprisingly graceful. The way two black holes spiral in, merge, and create something new is not a chaotic crash but a dance shaped by gravity and curved space. From Einstein's equations to LIGO's detections, the idea that two black holes can merge into one has gone from theory to observation. And as we continue to listen to the universe with gravitational wave detectors, we'll learn even more about these hidden giants and the cosmic symphony they create when they collide. Let your mind float gently in the vastness of space. Black holes, silent and invisible, may seem far away, but they remind us that even the most mysterious corners of the universe are connected by the same forces that hold you here, grounded on Earth. Sleep is only mentioned once tonight, and this is it. You're safe, and the universe is still humming its quiet, beautiful song. To truly appreciate the power and elegance of black hole mergers, we need to go deeper into how gravity works on this massive scale, and how Einstein's theory of general relativity changed the way we understand space and time. Before Einstein, gravity was thought of as a force pulling objects together, like the way the Earth pulls an apple down from a tree, or how the Sun keeps the planets in orbit. That's how Isaac Newton described it. But Einstein saw something more subtle and strange. He proposed that gravity is not a force in the traditional sense, but a bending of space-time itself. Imagine space and time as one interconnected fabric. Every object with mass bends this fabric slightly, and the more mass an object has, the deeper the bend. Black holes, with their immense density, don't just create dents in space-time. They form bottomless pits. Their gravitational pull is so extreme that they curve space-time into a funnel that nothing can escape from once crossed. When two black holes orbit each other, They're essentially circling within each other's warps in space-time, and with every orbit they disturb this fabric. These disturbances radiate outward as gravitational waves. They don't travel through space like light or sound. They are ripples in space itself, stretching and squeezing the universe as they move. If you could stand far away and watch two black holes spiraling in toward each other, you wouldn't see much with visible light, but you'd know that something powerful was happening. Their motion accelerates as they get closer, and the gravitational waves become stronger. In the final moments before they merge, the ripples they send out are violent enough to be detected here on Earth, despite being created over 1 billion light years away. And what do these waves look like? They aren't like ocean waves or sound waves. Instead, they change distances between objects ever so slightly. When a gravitational wave passes through an area, space itself stretches in one direction and compresses in another. If you had two rulers positioned at right angles and a gravitational wave passed through, one ruler would lengthen while the other would shrink, and then they'd reverse. This stretching and squeezing is incredibly tiny, far smaller than the width of a proton, but we can measure it. The detectors that measure these waves are marvels of precision. LIGO in the United States and Virgo in Europe use lasers and mirrors to track the slightest movements in space itself. When a gravitational wave passes through Earth, it causes a change in the distance between mirrors miles apart. A change so small, it's like detecting a shift smaller than a single atom over kilometers. It's amazing to think that the signals these instruments pick up originate from something as distant and powerful as two black holes colliding. And yet, when these detectors recorded their first wave in 2015, it matched perfectly with what Einstein's equations had predicted a century earlier. It confirmed that the merger of black holes was not just possible, it was real. But what happens during the actual moment of merger? For most of their lives, the black holes are in a gradual spiral, orbiting each other at increasing speed. But in the final few milliseconds, things become intense. The black holes move at a significant fraction of the speed of light. Their event horizons, the outer edges from which no light escapes, begin to distort, stretch, and finally touch. At that moment, the two event horizons combine into a single, larger horizon, forming a new black hole. The entire process is incredibly efficient. A few solar masses worth of material doesn't remain in the final black hole. It's been converted into pure gravitational wave energy, radiated away at light speed. In that brief instant, more energy is released than by all the stars in the observable universe combined. After the merger, the new black hole isn't perfectly stable at first. It rings like a struck bell, oscillating slightly as it settles into its final shape. This ringing also sends out gravitational waves, though they quickly fade. This phase is called the ring down, a beautiful term for a cosmic aftershock. Scientists study this ring down carefully because it tells us about the nature of the final black hole. Its mass, spin, and shape can all be determined by the specific patterns of those last waves. In a way, black holes have voices, but we don't hear them with ears. We detect their vibration through space itself. There's another fascinating detail to consider: the idea of spin. Black holes don't just have mass, they can also spin, and often do. When two spinning black holes merge, their final spin depends on how the individual black holes were spinning beforehand. If they spin in the same direction, the resulting black hole spins faster. If they spin in opposite directions or at an angle, the final spin is more complex, and sometimes causes the new black hole to wobble, like a top slowing down. And what about the shape? We often imagine black holes as perfectly spherical, but this isn't always true, especially during a merger. The event horizons can become distorted during collision, bulging or stretching under immense gravitational stress. But within moments of the merger, the new black hole stabilizes into the most efficient and minimal shape allowed by the laws of physics, a spinning sphere called a Kerr black hole. This natural tendency for black holes to simplify after chaos is one of the most elegant features of general relativity. Despite the violence of the merger, the final object is smooth, silent, and remarkably simple. No matter how complex the black holes were before, no matter how fast they were spinning, or what direction they moved in, the result is a single black hole, defined by just its mass and spin. That's part of the beauty of black hole physics. It strips away details and reduces everything to its essential properties. After all the complexity of motion, energy, and waves, you're left with something still and complete. These cosmic mergers don't just answer scientific questions, they open new ones. We've only just begun detecting these events. Every gravitational wave we capture is a message from a far corner of the universe, telling us that two black holes found each other and became one. They leave behind a story written in waves, etched into the shape of space itself. We'll keep listening to that story because each time we do, we learn not just about black holes, but about the nature of the universe and the laws that govern it. The more we understand how black holes merge, the more we understand how galaxies form, how time bends, and how energy moves through the cosmos. And in all this, we find something profound. The universe is not static. It's alive with motion, change, and growth. Even in the deepest darkness, where no light shines, there are great forces at work. And sometimes, two invisible giants meet, embrace, and become something new. When we talk about black hole mergers, it's easy to focus on the spectacle. The gravitational waves, the colossal energies, the collision of massive objects. But another fascinating question lies underneath. Where exactly do these mergers happen? What kind of environments lead to the collision of two of the most extreme objects in the universe? Let's start by looking at binary black hole systems, pairs of black holes that orbit one another. These can form in two main ways. They can be born together, or they can find each other later in life. When two massive stars form from the same cloud of gas and dust, they often do so as a binary pair. They orbit around a shared center of mass, locked in a gravitational relationship that can last millions of years. If both of these stars are heavy enough, they will each eventually explode in a supernova and collapse into black holes. If their explosions don't disrupt the system, and if they remain gravitationally bound, they'll continue orbiting each other as two black holes. This type of system is called an isolated binary, and it evolves gradually over time. Their orbits shrink extremely slowly due to the emission of gravitational waves. For most of their lives, these black holes are quiet, invisible partners spiraling ever closer. Then, in the final seconds of their existence, as separate objects, they collide and form one. The other way black holes can come together is through what's called dynamical interaction. In crowded regions like globular clusters or galactic centers, stars and black holes move in dense, chaotic patterns. In these environments, black holes can interact gravitationally with each other and with other objects. Sometimes these interactions lead to two black holes becoming gravitationally bound, forming a new binary system. This is like meeting a stranger at a crowded party and suddenly locking eyes forever. Not romantic, but gravitationally inevitable. These binaries form later in a black hole's life. and their orbits can be more eccentric or elongated. The way they spiral inward can be more erratic than those of the isolated binary systems. And then there are the truly titanic collisions, mergers between supermassive black holes. These giants, found in the centers of galaxies, are millions or even billions of times more massive than the Sun. When galaxies collide, which happens more often than you might think, their central black holes can eventually drift toward each other and merge. This process is much slower than the merger of smaller black holes. Supermassive black holes take an incredibly long time to coalesce. First, they fall toward the center of the new combined galaxy through a process called dynamical friction. Then they form a binary system, and eventually, if enough gas or stars are around to help them lose energy, they spiral closer and finally merge, creating an even more massive central black hole. These mergers are thought to play a huge role in galactic evolution. When two galaxies become one, their central black hole often becomes more active, pulling in surrounding matter and forming a quasar, one of the brightest and most energetic phenomena in the universe. So in a strange way, a black hole merger, an event that gives off no light itself, can lead to a dazzling beacon of energy visible across billions of light years. Scientists believe that nearly every large galaxy has undergone one or more supermassive black hole mergers in its history. The Milky Way is no exception. Our galaxy is currently on a collision course with the Andromeda Galaxy. In about 4 billion years, the two will merge, and eventually their central black holes will too. It's a slow process, unfolding on timescales far beyond a human lifetime, but it's part of the long cosmic rhythm of creation and destruction. There's also growing interest in something called intermediate mass black holes, objects heavier than stellar black holes but lighter than supermassive ones. These have been harder to detect, but recent gravitational wave events have hinted at their existence. When two stellar mass black holes merge, the resulting black hole may fall into this intermediate range. And if those intermediate black holes go on to merge again, they could help explain how the supermassive giants came to be. This gives us a kind of black hole family tree. Smaller black holes form from stars. Those can merge to create larger black holes. And over time, through repeated mergers, the most massive black holes we know, the ones anchoring galaxies, may have grown from these smaller ancestors. It's a cosmic ladder with merging black holes as the rungs. But how often do these mergers happen? With the help of gravitational wave detectors like LIGO and Virgo, we're starting to get an answer. Since the first detection in 2015, dozens of black hole mergers have been recorded. The data suggests that these events are surprisingly common, possibly occurring every few minutes somewhere in the observable universe. Most of these are too far away or faint for us to detect directly, but as our instruments improve, we'll be able to see farther and catch more of these ripples in space. Future detectors like LISA, the Laser Interferometer Space Antenna, will orbit the Earth and be able to detect lower frequency waves, opening a new window into supermassive black hole mergers. And there's another fascinating possibility. Some black hole mergers may create conditions that briefly allow for the emission of electromagnetic radiation, light. This is rare since black holes don't emit light themselves. But if the surrounding environment is rich with gas, the merger can disturb it, heating it up and causing it to glow. In some cases, telescopes may be able to see a flash or flare of light at the same time a gravitational wave is detected. This kind of multi-messenger astronomy, where we detect an event through both gravitational waves and light, is one of the most exciting developments in modern astrophysics. It's like hearing and seeing the same event at once, giving us a fuller picture of what's happening in deep space. So when two black holes merge, it's more than just a collision. It's part of a grand, ongoing process, one that shapes galaxies, affects the growth of cosmic structures, and leaves behind clues for us to decode. These events connect the death of stars to the architecture of the universe. From crowded star clusters to the hearts of galaxies, the universe provides many different stages for black holes to find one another. And when they do, the result is always the same: a single, larger black hole and a wave of energy that carries their story across the cosmos. Now that we've explored where black hole mergers happen, let's take a closer look at what happens in the very final moments of the merger. The last few seconds before two black holes become one. These final instants are among the most extreme, energetic, and fascinating events in all of physics. Picture two black holes spiraling around each other. For most of their shared existence, their orbit is wide and slow. Over millions of years, they gradually draw closer, their motion tightening into a graceful spiral. But as they near the final stages, everything accelerates. Their orbital period, the time it takes for them to circle each other, shrinks from hours to minutes, and then to mere seconds. The gravitational waves grow more intense, more frequent, and far more powerful. In the final milliseconds, the black holes are traveling at close to the speed of light. Their event horizons, the invisible boundaries beyond which nothing escapes, begin to stretch and distort. The two black holes are no longer neat spheres. They become elongated, like water droplets about to merge. At this stage, their gravitational fields begin to overlap. Space and time between them are warped almost beyond recognition. The gravity is so strong that it's no longer accurate to say they are orbiting. They are collapsing inward, locked in a final embrace. Then, contact. The two event horizons touch and instantly begin to fuse. There is no explosion of light, no burst of matter, just the sudden appearance of a new, single event horizon, enclosing both original singularities. What moments ago were two separate points of no return are now one, encircling a new black hole. This newly formed black hole doesn't immediately settle into a perfect sphere. Instead, it vibrates. These vibrations are incredibly subtle, but they radiate gravitational waves into space. The ring-down phase. Imagine striking a bell and hearing it hum gently as it fades into silence. That is what the black hole is doing, except it hums not with sound, but with waves in space-time. These final waves carry a tremendous amount of information. From their pattern, scientists can determine the mass and spin of the final black hole. They can even test whether the object that formed behaves exactly as predicted by Einstein's general relativity. And so far, every single observed merger has matched the theory perfectly. The ring-down stage is also important for a concept called the no-hair theorem. This idea says that black holes are incredibly simple objects. Once formed, they have only three measurable properties: mass, spin, and electric charge. Since most black holes have negligible charge, that leaves only mass and spin. No matter how complicated the merger, the result always simplifies into a black hole with just those two traits. It's a bit like burning a complex sculpture. No matter what shape it had before, all that remains is heat and ash. In the case of black holes, all that remains is mass and spin. But the story doesn't quite end there. Depending on the asymmetry of the merger, if one black hole was significantly larger than the other, or spinning at a different angle, the final black hole can experience something remarkable: a recoil. Gravitational waves carry momentum. If more waves are emitted in one direction than the other during the merger, The new black hole experiences a push in the opposite direction. This recoil can be small, just a gentle drift through space, but in extreme cases it can reach thousands of kilometers per second. A black hole kicked at that speed could be ejected from its host galaxy entirely, flying off into intergalactic space. It's a dramatic image, a silent, invisible giant flung across the cosmos, all because of a lopsided burst of gravitational energy. Astronomers have even found hints of this happening. Some galaxies appear to have central black holes that are offset or missing, possibly the result of a powerful recoil from a merger long ago. And as our instruments improve, we may one day directly observe a recoiling black hole on the move. The final product of a merger, a larger, spinning black hole, is stable, but it's not necessarily the end of the story. That black hole may one day encounter another. In the densest parts of the universe, mergers can happen again and again, forming increasingly massive black holes over time. This stacking of mergers could explain the mysterious intermediate mass black holes, objects too large to have formed from a single star, but not large enough to be called supermassive. In star clusters, for example, repeated mergers could gradually build up a black hole hundreds or even thousands of times the Sun's mass. And if such a black hole finds itself in a galaxy, pulled toward the center over time, it could eventually join with the central supermassive black hole, contributing to its growth. This process, mergers building on mergers, is part of how we think the largest black holes in the universe came to exist. It's a kind of cosmic construction, layer by layer, across billions of years. It's worth pausing to appreciate how much of this we now know because of gravitational wave astronomy. Just a few decades ago, black holes were purely theoretical. We couldn't see them directly, and we had no way to observe them interacting. Today, we can listen to their collisions. We can measure their masses, spins, and even estimate how far away they are, all from the gentle stretching of space. And all of this begins in those final seconds. The climax of a black hole merger, though brief, is rich with data. Each wave is a signal from a place we can never visit, a whisper from a dark, distant event, telling us that two objects became one. What seems like a violent end is actually a beginning. A new black hole now exists where two once orbited, and somewhere, far away, space is still settling after the tremor. A reminder that even in the deepest darkness, motion, change, and connection are possible. We've talked about what happens when two black holes merge, the gravitational waves they produce, the final moments before fusion, and the birth of a new black hole. Now let's explore how we actually detect these events from here on Earth, and why that detection has changed the course of astrophysics. To begin with, detecting a black hole merger is not like seeing a star through a telescope. Black holes do not emit light. They don't shine, reflect, or even glow. So traditional optical telescopes are blind to them. That's where gravitational wave detectors come in. The most well-known of these is LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO has two main facilities in the United States, one in Hanford, Washington, and one in Livingston, Louisiana. A third major detector, Virgo, operates in Italy, and more are planned or under construction around the world. These observatories don't use lenses or mirrors in the traditional sense. Instead, they rely on a precise measurement system called laser interferometry. Each detector has two long arms set at right angles, often stretching several kilometers in length. A laser beam is split and sent down each arm, where it bounces off mirrors and returns to a central point. If a gravitational wave passes through the Earth, It stretches space in one direction and compresses it in the other. This changes the distance the laser travels by an amount smaller than the width of a proton, but even that tiny shift is enough to be detected by the ultra-sensitive instruments at LIGO and Virgo. When the first detection happened on September 14, 2015, it was a moment that had been anticipated for decades. The signal matched exactly what was expected from the merger of two stellar mass black holes. It was brief, lasting less than a second, but contained more information than anyone could have imagined. Since then, dozens of mergers have been recorded. Each one is like a fingerprint, unique in its mass, its spin, and its distance from Earth. Some events involve nearly equal mass black holes, others involve large differences. Some spins are aligned, while others are chaotic, and all of them tell us something new about how black holes live, move, and collide. Gravitational wave detectors have opened an entirely new way to study the universe. In the past, astronomy relied solely on electromagnetic radiation, visible light, radio waves, X-rays, and so on. Gravitational waves offer a new kind of signal, one that travels unhindered through space, unaffected by dust, gas, or electromagnetic interference. Think of it this way. Before gravitational wave astronomy, we were watching the universe. Now we're also listening. And the universe has a lot to say. The detectors have also allowed us to test some of the deepest principles in physics. For example, we can use black hole mergers to test Einstein's theory of general relativity under extreme conditions. So far, the predictions match perfectly. But if even the tiniest discrepancy were ever found, it could point to new physics, perhaps a deeper theory of gravity that extends beyond general relativity. One of the most intriguing possibilities is using black hole mergers to study the expansion of the universe. When we detect a gravitational wave, we can estimate how far away the event was. If we also see a light signal from the same event, as we did in a neutron star merger in 2017, we can compare distances and redshifts, helping refine our measurements of the Hubble constant, which describes the rate of cosmic expansion. In this way, black hole mergers become cosmic yardsticks, helping us map the universe on the largest scales. And while we've mostly focused on stellar mass black holes so far, future detectors will expand our reach to even larger events. Projects like LISA, a space-based gravitational wave observatory planned by the European Space Agency, will detect lower frequency waves from massive objects, including supermassive black hole mergers. LISA will consist of 3 spacecraft in a triangle millions of kilometers apart, orbiting the Sun. Its enormous size will allow it to detect gravitational waves with longer wavelengths, the kind produced by black holes millions of times the mass of the Sun. These waves move slowly and steadily, sometimes taking hours or even days to pass by, but they carry rich information about the most massive objects in the universe. Imagine listening to the slow, deep chime of 2 galactic giants spiraling into one another, their vibrations echoing across the cosmos for billions of years. That's the kind of data LISA will provide. In the meantime, LIGO and Virgo continue to detect new events, each one a reminder that the universe is constantly moving, changing, and merging. Some signals are loud and clear, others are faint whispers from the edge of detectability. But together, they form a growing catalogue of black hole behavior, a database of cosmic collisions. And every time we detect a new merger, we add another point to our understanding. We learn how often black holes merge, how their masses are distributed, how they spin, and what environments they came from. We even begin to understand how galaxies evolve, since black hole activity often shapes the formation and motion of stars around them. In just a few short years, gravitational wave astronomy has gone from theory to practice, from the dream of physicists to a daily reality. And black hole mergers are at the heart of it all. It's remarkable to think that, for all their mystery, black holes can now send us signals that we can read and interpret. Their collisions, once hidden forever in the darkness, now speak to us through the structure of space itself. These aren't just exotic curiosities, they are fundamental parts of the cosmic story, telling us about matter, motion, energy, and time on the grandest scales imaginable. And they remind us that even in the deepest silence of space, there is rhythm, motion, and a kind of cosmic music. We are only at the beginning of this journey. With each detection, we get better at listening. And with each black hole merger, the universe tells us just a little bit more about itself. Now that we've looked at how we detect black hole mergers and the revolutionary role of gravitational wave astronomy, let's turn to another important question. What can black hole mergers tell us about the history and structure of the universe? At first glance, it might seem like these mergers are isolated events, two black holes colliding in some distant corner of space. But in reality, they are deeply connected to the overall evolution of the cosmos. Every merger we detect is not just a local interaction, it's part of a much larger story. The growth of galaxies, the life cycles of stars, and the very fabric of space and time. To understand this, we need to go back in time, not just years or centuries, but billions of years, to the early universe. Shortly after the Big Bang, the universe was hot, dense, and filled with light elements like hydrogen and helium. Over time, this matter began to clump together under the force of gravity. These clumps formed the first stars, massive, short-lived giants that burned bright and ended their lives in powerful explosions. These first generations of stars were different from the stars we see today. They were larger, hotter, and often more unstable. Many of them may have collapsed directly into black holes after death. Some of those black holes merged, forming larger ones. And over time, they became the seeds of the massive black holes we see in the universe today. This process, the repeated merging of black holes, is thought to be a key mechanism behind the growth of supermassive black holes in galactic centers. As galaxies formed and evolved, so did the black holes at their cores. Each time two galaxies merged, their central black holes were drawn toward each other, forming a binary system. Eventually, they too would merge, repeating the process again and again. These central black holes influence their surroundings in powerful ways. They can affect star formation, control the flow of gas, and even shape the structure of the galaxy itself. Through their gravity and energy, they help determine how a galaxy grows, what shape it takes, and how it evolves over time. So when we observe a black hole merger, even if it's billions of light years away, we are witnessing a key step in this cosmic evolution. We're seeing how structure is built in the universe, not just through the birth of stars and galaxies, but through the union of dark, invisible giants. But the implications go beyond just galactic history. Black hole mergers also give us insight into the very nature of time and space. Gravitational waves stretch and compress space-time as they pass, offering a direct test of how gravity behaves on large and small scales. They travel at the speed of light, unaffected by matter, which allows them to carry information from the distant past, clean and unfiltered. When we detect a merger that occurred over 1 billion light-years away, we're not just learning about two black holes. We're looking back in time, seeing how the universe behaved when it was younger. This is one of the most powerful tools we have for understanding the history of the cosmos. Gravitational waves are also helping us explore some of the most mysterious questions in physics, questions that lie at the boundaries of our knowledge. For example, do black holes obey the same quantum rules as particles? What happens at the singularity, the point of infinite density inside a black hole? Are there deeper theories of gravity that go beyond general relativity? Some researchers even speculate that black hole mergers might reveal signs of extra dimensions or hidden particles. These ideas are still highly theoretical, but with each new observation, we get a little closer to testing them. There's also the question of dark matter, the invisible substance that makes up most of the matter in the universe. Some theories suggest that dark matter might clump around black holes or influence how they form and merge. Others propose that black holes themselves could be made of dark matter, or that tiny primordial black holes formed in the early universe could be a component of it. If we can better understand how black holes merge, where they form, and how often they appear, we may find clues about the nature of dark matter and its role in the cosmos. And it doesn't stop there. Black hole mergers might also help us understand the large-scale structure of the universe, the cosmic web of galaxies and voids that stretches across billions of light years. These mergers trace the locations of massive objects, mapping where black holes are found, and by extension, where galaxies and matter are concentrated. So, in a way, every merger is like a pin on a map. Each one tells us where matter has collected, where stars once lived and died, and where gravity has done its work over time. By collecting enough of these pins, enough merger events, scientists can build a more complete picture of how the universe is shaped. It's like connecting the dots in a giant cosmic drawing, with each dot representing a moment of transformation. Two black holes becoming one. This brings us back to one of the most profound themes in modern physics: unity. Over and over again, nature shows a tendency to combine, to bring together smaller parts into larger wholes. Atoms form molecules. Molecules form stars. Stars collapse into black holes. And sometimes those black holes come together to form something new. Each black hole merger is an echo of this pattern, a quiet affirmation of the universe's tendency toward connection and structure. It's poetic in a way. Two invisible remnants of long-dead stars, drawn to each other across the vastness of space, finally spiral together and become one. The moment passes quickly, but its effects ripple across time, changing the shape of the universe ever so slightly. And even though we can't see it directly, we can now hear its whisper, a gravitational signature traveling through space-time, reaching our detectors here on Earth, telling us that somewhere far away, the universe just got a little bit more unified. As we follow the path of black hole mergers through space and time, it's natural to wonder, what happens after the merger? The two black holes are now one, their event horizons fused, their singularities joined. The gravitational waves have been emitted, the surrounding space has calmed. But the story doesn't end there. The aftermath is just as intriguing. The new black hole formed in a merger is not always still. As we've explored, depending on the asymmetries in the collision, differences in mass, spin, or direction of motion, the resulting black hole might receive a kick. This gravitational recoil can send it moving at high speed, sometimes hundreds or even thousands of kilometers per second. If this event occurs in the outer regions of a galaxy or in a smaller galaxy with weaker gravitational binding, that kick might be strong enough to eject the black hole entirely. It could leave the galaxy and enter intergalactic space, an enormous, dark void with few stars and little matter. Imagine a lone black hole silently gliding between galaxies, carrying the memory of its origin in the ripples of space it left behind. These so-called rogue black holes are difficult to detect, but they may be out there, scattered throughout the universe, leftovers from violent cosmic unions. But most merged black holes remain within their galaxies, especially if the merger happens in a dense region like a galactic center. In these environments, the black hole might quickly begin to interact with the surrounding gas, dust, and stars. If enough material is nearby, it can begin to accrete matter, pulling it in with its gravity. As this matter spirals inward, it heats up and emits energy, sometimes forming a glowing accretion disk. If the infalling material is plentiful, the black hole might even power a quasar, one of the most luminous phenomena in the universe, so paradoxically, the merger of two lightless objects can result in an outburst of light that travels for billions of years. This transformation from silent merger to brilliant outburst is one of the many ways black holes affect their environments. They don't simply sit at the centers of galaxies. They shape their neighborhoods. The energy released by an accreting black hole can heat surrounding gas, drive outflows of matter, and regulate the rate of star formation. It's a kind of feedback loop. The black hole grows, but also influences how the galaxy evolves. Some black holes formed from mergers may go on to merge again. In dense environments like star clusters or galactic centers, collisions can happen multiple times over cosmic timescales. Each time, the resulting black hole becomes more massive. This process of successive mergers might explain the existence of intermediate mass black holes, those too large to be formed in a single stellar collapse, but too small to be considered supermassive. Over time, through repeated interactions, a single black hole could climb the mass ladder, growing larger with each merger. Eventually, such a black hole could drift toward the center of a galaxy and merge with the supermassive black hole already there, contributing to its growth and changing its properties. The life of a black hole, in this way, is not a simple path. It's filled with transformation, interaction, and motion. Even though nothing can escape from a black hole once it enters, black holes themselves are not frozen or static. They are dynamic parts of the universe's ecosystem. One interesting aspect to consider is how black hole spin evolves through mergers. Spin is a fundamental property, a measure of how quickly a black hole rotates around its axis. When two black holes with different spins merge, the resulting spin of the new black hole depends on the direction and magnitude of the original spins. Sometimes the result is a fast-spinning black hole. Other times, the spins partially cancel, and the final object spins more slowly. This spin affects the shape of the event horizon and how the black hole interacts with matter and space around it. A spinning black hole can twist space-time, a phenomenon called frame dragging, pulling nearby objects into motion around it. Over time, this spin can be altered by new material falling in or by future mergers. So even after a black hole has formed, it continues to evolve, subtly influenced by its cosmic surroundings. And then, there's the gravitational memory left behind. When two black holes merge and send gravitational waves across the universe, they permanently alter the shape of space-time. It's a tiny, frozen imprint, a slight distortion that remains long after the waves have passed. This is called the gravitational memory effect. It's as if space itself remembers the passage of the wave, even after the event is over. This effect is extraordinarily small and difficult to detect, but it's one of the more poetic ideas in physics, that space itself holds the memory of cosmic events. like the faint imprint of a footstep left in the sand. In the far future, the new black hole formed by the merger may continue to drift through space for trillions of years. It might interact with other stars or black holes, or it might remain isolated. Eventually, over unimaginable timescales, if Hawking radiation is real, it could slowly evaporate, shrinking bit by bit until it disappears. This evaporation process is theoretical, but it's one of the few possible ways black holes might end. If true, it means even the quietest remnants of black hole mergers might one day fade entirely, leaving only the memory of their ripples in space-time. For now, we are at the very beginning of understanding this long arc. We're just learning how to detect the mergers, trace their origins, and map their effects. But even in these early days, the story is already rich with wonder. What starts as a quiet collision between two invisible objects ends up shaping galaxies, influencing stars, and helping us understand the deepest laws of nature. Black holes, often thought of as cosmic endpoints, are also part of a larger cycle, one that stretches from the hearts of stars to the edges of space and time. Their mergers are moments of transformation, not endings, and each one leaves a subtle, lasting mark on the universe. As we continue our journey through the life and union of black holes, it's worth turning our attention to a concept that challenges the edges of what we think we know: the singularity. What exactly happens at the core of a black hole, and what does it mean when two singularities collide? At the heart of every black hole is a region known as the singularity, a point where matter is thought to collapse into infinite density, where space and time no longer behave as we understand them. According to Einstein's theory of general relativity, this is where the equations break down. It's not that we have a clear picture of what's inside, it's that our current physics simply cannot describe it. The singularity is surrounded by the event horizon, the boundary beyond which nothing can escape, not even light. While the event horizon can be measured, shaped, and modelled, the singularity remains hidden, unreachable, and deeply mysterious. So when two black holes merge, their event horizons combine, and beneath that, their singularities also coalesce. But because the singularities are concealed by the horizons, we don't know exactly how this inner fusion plays out. It's a place where our understanding reaches its limits. Some physicists believe that singularities are not truly physical, that they are artifacts of incomplete equations. Perhaps in a more complete theory, such as quantum gravity, the singularity would be replaced by something else, a highly dense but finite region, or a new form of matter or energy. If that's the case, then a black hole merger might involve the collision of these exotic inner structures, something far stranger than anything we currently imagine. Others propose that the singularity might be a gateway of sorts, a one-way passage to somewhere else. This leads to ideas like wormholes and white holes, speculative concepts that have not been observed but are permitted by certain interpretations of Einstein's equations. A wormhole is a tunnel through space-time, a bridge connecting two distant regions of the universe. A white hole, in contrast, is a hypothetical object that is the reverse of a black hole. Nothing can enter it, but matter can escape from it. In some theories, a black hole's singularity might be linked to a white hole elsewhere, creating a strange passage through the cosmos. These ideas are highly theoretical and not supported by current evidence, but black hole mergers provide a rare and powerful opportunity to test some of these possibilities. If a merger produced unexpected gravitational wave signatures, if the waves behaved in a way that didn't match Einstein's predictions, it might hint at something new happening inside. So far, the waveforms we've detected have matched perfectly with what general relativity predicts. But physicists continue to look closely, searching for the tiniest discrepancies, because within those subtle details, we might find hints of the quantum nature of gravity or clues about what really lies inside a black hole. Some researchers are exploring the idea that black holes could be fuzzballs, quantum objects without a singularity, made up of tangled strings of information, as described by string theory. In this view, black holes have no hard surface and no central point. Instead, they are complex, quantum systems that only appear smooth from a distance. This would mean that when black holes merge, what's really colliding are two clouds of quantum information, not two classical singularities. The result would still behave like a larger black hole from the outside, but internally, the process could be very different from what general relativity describes. One of the deepest mysteries connected to all this is the black hole information paradox. When a black hole forms, it absorbs everything inside it: matter, energy, even information. According to quantum mechanics, information cannot be destroyed. But if a black hole eventually evaporates, where does the information go? Stephen Hawking's famous work on black hole radiation raised this troubling question. He proposed that black holes emit tiny amounts of radiation over incredibly long periods of time, a process that would eventually cause them to disappear. But if they vanish completely, what happens to the information about what went in? Does it somehow escape with the radiation? Does it remain encoded in the event horizon? Or is there a deeper principle we're missing, one that unites gravity and quantum physics in a way we don't yet understand? Merging black holes may help us answer this. If we can understand how their horizons behave, how information might be preserved, and how quantum effects could influence the merger, we may begin to bridge the gap between our two greatest theories: general relativity and quantum mechanics. The search for a theory of quantum gravity, a framework that unifies the very large and the very small, is one of the greatest goals in modern physics. And black holes, especially when they merge, are the perfect laboratories for this search. They push physics to the limit. They test our understanding of space-time, mass, energy, and information. And they remind us that even the most extreme events in the universe are still governed by rules, even if we haven't discovered all of them yet. It's humbling to realize how much we don't know. Black holes challenge our assumptions. They stretch our imaginations. And they invite us to explore not just outer space, but the very foundations of reality itself. So when two black holes merge, we are not just witnessing a cosmic event, we are peering into a mystery that touches the very core of physics. We are listening to a moment where our current understanding fades, and where something deeper, perhaps stranger, begins. And that is part of the quiet wonder of black hole mergers. They are more than just collisions. They are questions. Questions written into the fabric of space, carried on the waves of gravity, waiting for us to listen closely and discover what lies beneath. By now, we've traveled across time and space, from the first stars to gravitational wave detectors on Earth, following the story of how black holes can find each other and merge. But let's slow down and look at an even deeper layer: the philosophical and cosmic implications of black hole mergers. What do they mean beyond physics and astronomy? What do they say about the nature of the universe itself? Black holes are the most extreme objects we know. They represent a point where gravity becomes so strong that the normal rules of reality, of space, time, and even causality, begin to dissolve. In this sense, they are not just cosmic objects, but boundaries of knowledge. When we study them, we're not just learning about distant parts of the universe, we're testing the very limits of human understanding. When two black holes merge, it's as if the universe itself is speaking in its quietest, most powerful voice, a whisper that stretches across billions of light years, a signal that begins with death, the collapse of stars, and ends with unity. There's something poetic about that. Stars that lived for millions of years burn out and collapse. They vanish into black holes, and after untold time, they drift close to another, orbit, spiral, and merge. The process is slow and silent, invisible for nearly its entire lifetime, and yet in its final second, it becomes one of the loudest events in the universe, not through light or sound, but through the warping of space itself. And we, tiny beings on a small planet, can now detect that signal. We can know that something invisible and ancient happened long ago in a galaxy far away. That awareness, that connection, is a triumph of human curiosity. There's also something deeply symbolic about the act of merging. Two distinct entities, each defined by their mass, spin, and motion, becoming one. Their individual characteristics combine into a single whole, and their pasts are carried forward, encoded into the new black hole's properties. But the details of who they once were are no longer distinguishable. In the language of physics, this is the no-hair theorem again. The new black hole has no memory of the complexity of its predecessors, only their combined mass and spin. But as a metaphor, it speaks to something broader, the way the universe is constantly combining, evolving, and simplifying. From atoms to stars, from galaxies to black holes, nature favors structure. It favors unity. Even destruction, in the form of a merger, leads to something new, something stable, something lasting. It's fascinating to think that black hole mergers are not rare events. They happen constantly, across the observable universe. At any given moment, somewhere in space, two black holes are spiraling closer. Right now, as you listen, perhaps dozens of black hole mergers are happening. They're gravitational waves on their way to Earth. Silent, steady ripples traveling through the dark. In a way, the universe is never still. Even in the blackness between galaxies, change is unfolding. And yet, despite their power, black holes do not dominate the night sky. They're invisible. Their presence is inferred, not seen. It takes deep understanding and advanced tools to detect them. But once we know how to listen, they become impossible to ignore. This subtlety is part of their beauty. Black hole mergers don't announce themselves with fire or brightness. They move through the universe quietly, elegantly, changing everything around them without needing to be seen. There's a lesson in that some of the most important events are not the loudest or most visible. That profound transformation often happens in silence, and that even the most hidden processes can leave a lasting mark. From a cosmic perspective, black holes are nature's way of balancing the books. They gather mass, collapse space, and conserve information in strange and mysterious ways. And yet, despite their reputation as destroyers, they are creators too. Creators of gravitational waves, of galactic architecture, of mysteries that challenge the sharpest minds. There's also the question of time. Black holes distort time. Near the event horizon, time slows relative to an outside observer. In the frame of reference of the black hole, the merger happens quickly, in seconds or less. But from another perspective, near the edge, time appears to slow infinitely. It's as if black hole mergers blur our very concept of when. That idea alone, that different observers can disagree on how time flows, reminds us that the universe is not built according to our everyday intuition. It's more flexible, more complex, and in some ways more beautiful than it seems. We often imagine space as vast, cold, and empty. But black hole mergers tell a different story. A story of connection, of invisible forces binding distant objects, of silent waves carrying messages across light years. The universe is full of these quiet conversations, moments of interaction written in gravity. And finally, there's the feeling of awe. When you consider the scale, the energy, and the mystery of black hole mergers, and the fact that we can detect them, it's hard not to feel something deeper, a sense of wonder maybe, or humility, that something so immense and powerful is even knowable, that we, as observers made of stardust, can uncover its patterns, is a quiet miracle. So, when two black holes merge into one, it is more than an event in the sky. It is a moment of meaning, a sign that the universe continues to evolve, that complexity can become simplicity, and that the invisible can still speak. And somehow, that story reaches all the way to here, to us. We began with a question: can two black holes merge into one? And now we know that the answer is yes. Not only can they, but they do. All across the universe, all the time. From the collapse of massive stars to the rippling waves of gravity across space-time, black hole mergers are woven into the fabric of cosmic evolution. We've explored how these mergers happen, from binary systems slowly spiraling inward to the final seconds of collision. We've looked at the power of gravitational waves, silent ripples in space itself, and how they let us listen to these otherwise invisible events. We've followed the journey from massive stars to dark remnants, to collisions that warp space and time, to the formation of a new black hole, a single, larger object that carries within it the history of both its predecessors. We've gone deeper into how we detect these events here on Earth using advanced observatories, and what those signals tell us about the nature of black holes, the growth of galaxies, and the shape of the universe itself. We've stepped beyond physics into philosophy, asking what it means to have something infinite at the heart of a black hole, how quantum and classical theories may one day meet, and how even the most silent events can leave behind echoes that shape the cosmos. And perhaps, most of all, we've simply paused to appreciate the beauty of it all. The quiet merging of two invisible giants, the waves that whisper their message through the darkness, and the way our small blue planet, tucked into one corner of space, can feel those whispers and understand them. Black hole mergers are more than just astronomical events. They are a kind of cosmic poetry. They remind us that the universe is not static. It is alive with motion, with rhythm, with union. Stars are born and die. Black holes drift and collide. Space stretches, bends, and carries their story.
And we, observers, thinkers, dreamers, get to witness that story piece by piece.
So, as we come to the end of tonight's exploration, take a moment to breathe deeply, to feel the vastness of what we've touched. Two black holes circling in silence. The final spiral, the fusion into one. And the gentle waves traveling billions of years just to reach you. It's humbling, it's beautiful, and it's real. Thank you for spending this time with us here on SleepSpace. Whether you're now resting peacefully or still awake and thinking, I hope this journey brought you a sense of calm, curiosity, and quiet wonder. Until next time, good night, and may your dreams drift as gently as gravity.